Thank you all for being here. My name is Christina Lee, and I am an Android engineer at Pinterest. And if you've seen some of my former talks, I've done a modified version of this talk. It was shorter, fit into 20 minutes. The material was really well received, so I wanted to expand on that. So I'm going to cover some of what I've talked about before, bear with me, but I'm also going to dive a little deeper into areas I previously didn't have time to talk about. So with that, I just want to start by looking at the Kotlin type system. The reason for that is that so much of the good things that Kotlin gives us comes from the type system. Now, if you've never seen a visual representation of what the Kotlin type system looks like, it's something like this. Two things to point out is down there at the bottom, we see the nothing type, and everything flows from the nothing type. It is the subtype of all types. Up at the top, we have any question mark, and everything culminates in any question mark. It's the super type of all types. And then in between, we have our primitives, if we want to call them that, like int. And then we also have children and parent classes in the way we would assume. So this is the shape of the type system. It's very neatly ordered. There are no exceptions here. Now, a note before we go any further, I think we as developers often use the word class and type interchangeably. And that's actually not correct. In some cases, it can be correct. For instance, in this line, this first line, we have class is string, and so is the type. As soon as in Kotlin you introduce the idea of nullability, though, the class and the type, they start to diverge. So in this second line, string is still the class, but string question mark is now the type. And if you go further and do anything at all with collections, you get into a situation where the same class will generate nearly infinite types. In these three examples, the class is always list, but as you can see in the third line, the type is a list of a pair of an int of a list of a string. So, with that, let's go ahead and take a look at why we care. And I always make the same joke, which is that I must acknowledge nullability in any talk I do about Kotlin, so here it is. Why do we care about having a really orderly type system? Well, we're all used to behavior like this, wherein we can assign something that's an int to something with a type number, and we can do that because we have a subtype to supertype relationship. Well, the same thing gets us null safety. So here, if we declare something that's nullable and we try to assign it to something that's not nullable, it's not going to compile. And the reason for that is it breaks the exact principle that we have in this line, which is if you remember that type diagram, string is the subtype of string question mark, but not the other way around. So we get null safety, which we all know and love. Yay for types. Now, let's take a look at some of those other areas just to establish a basis. You saw the nothing type there, and you might wonder why you care. I mean, it's kind of cool. It's a fun word. And the reason, in short, of why we care about the nothing type is code like this. If you've used Kotlin, you might have used this function to do. Why would you use it? Well, if you don't have it, you immediately get a compilation error. You have some declared return type, you're not fulfilling it, and you need to before you can compile. But if you're building out your code and you don't want to have to do this just yet in order to get the compilation, then you might go ahead and do something like to do. Now, this should beg the question, why does this work? Like, what magic is happening under the hood that suddenly lets me compile code that doesn't actually have the return type I'm requesting? And the answer is, well, this is the magic. So in short, what is the to-do function? It's a function that only throws an error. That's all it does. It throws an error. And what is the return type? Well, the return type is nothing. Now, this may seem a little strange, but we're actually used to this behavior already. So in a line like this, where we take in something nullable, and then we use this Elvis operator to say, if it's not null, use this value. If it is null, do this thing over here. Well, we know that we are short-circuiting the logic because then on the very next line, we can use that as a not null type. Now, if we got rid of this check, and then we try to do something with the nullable, it's going to give us that error. You can't do that. It's not safe. But if we have this value, like so, and we throw, then we can use it as if it's not null. And the reason for that is that because the compiler knows that you'll never reach that second line, because if it is null, the program would have thrown the exception and short-circuited. Well, to-do and the nothing type, that's exactly what they represent. They represent the notion that a function will never complete normally. And so in this code, you'll actually see that on the left-hand side, it says that it's unreachable. The reason for this is because to-do returns nothing, and nothing means that it will never complete normally. Ergo, you will never reach that assignment because as soon as you go and try to evaluate the to-do function, you're going to get an exception and it's going to stop. That's why this code on the left-hand side is unreachable. So that's to-do. It represents the idea that anywhere that you have this nothing type, the code will never complete normally. Okay, taking a look at any versus object, we get a lot of questions about this. Any is the default supertype of a class. You can declare a class like this. This is valid code. But you can also declare it like this and give it an explicit supertype. So these are equivalent. Now, there's also this nicety around any, which is that our primitive system to us as end users appears exactly the same as our reference type system. So in Java, you might be used to having value types and reference types, and those diverge. But in Kotlin, that's handled for us. So under the hood, that is all still happening. But as far as we're concerned, everything is acting in a linear way as a reference type that bubbles up to any. So if we have an integer like this, which would be a primitive in Java, we can still assign it to any. So again, there are no exceptions to this. Under the hood, we have that boxing and unboxing going on, but we don't have to deal with that. Now, any is not the same as object. At runtime, you're going to see an object there, but it's different because it's screened. So if you look at the declaration for any, you see this is it. This is all that there is there, and it has exactly 3 functions, which is hashcode, equals, and toString. Now, object, on the other hand, has a lot more than that. For instance, it has this notify function. If you try to use object in Kotlin, it's immediately going to tell you that's a really bad idea. The idea of any is not that you're using this for complicated logic. It is usually just a subtype to, or a supertype to something else you care about. So using object in Kotlin is a no-no. You should try to avoid it, but you can because these things are based on the same implementation. Now, I always call this out because sometimes there's confusion about any. Any is indeed the default supertype of classes, but it is different from any question mark. Namely, you cannot assign something that's any question mark to something that's any. It's not an exception. The type system is rigorous. There are no exceptions to this shadowed null hierarchy. Okay, unit. This is the part that I find really, really fun. I've inserted this huge block quote here. You don't need to read it. You can. It's a great quote, but you don't need to because I'll go through the pieces of it. Basically, the gist of this is that unit and void more or less represent the exact same concept. And that concept is that whatever function returns those two things is there only as a side effect. If it wasn't a side effecty function, it would return a value. Because it's not returning anything, it must be printing to the console or hitting the network or modifying the database or some other side effecty functionality. And so that's why you use void and unit. That's what the concept exists for. But there's a difference in how that concept is implemented. Namely, void is the idea that you return absolutely nothing. If a function is, public static void main, you're returning nothing from that function. Unit is the idea that you return nothing useful. And I know that sounds super arbitrary and like, okay, why do we even care? That's ridiculous. And the reason we care, in short, is generics. Because unit, if you go in and look at it, this is the declaration, and they take that doing nothing nothing useful thing very seriously. Like the only thing you can do is if you have unit, you can print it. That's all you get from this. You'll also notice that it has the object keyword, which in Kotlin represents a singleton. So there's one instance of this thing floating around, and the only thing that instance can do is be printed to the console. So it really doesn't do anything useful. But it has exactly the same form as everything else in Kotlin. And because of that, we can use it in generics in a way that we couldn't with void. So with void in Java, you may notice that you have to use a capital V void type if you want to use it as a parameter to a generic. This isn't awful, but it does mean that you can't use that keyword that you're used to using in all of your functions. And namely, you have to go in and start changing the return types and then explicitly returning the type parameter of capital V void. Now with unit, none of that has to happen. We return unit by default, so here I've done it explicitly, but you don't need to do that. You can do this and it's exactly equivalent. I can store it as a parameter somewhere. I can use it as a type. Nothing changes. Unit is an object just like anything else. It's a class with a single instantiation, so I can use it the same way I would use any other generic parameter. And that's nice because it gets us something like this. I'm not doing lowercase u unit and uppercase u unit. I'm just doing unit. Nothing changes. And so this is nice. It's not the end of the world to do this with void, but it's a little less than ideal. Okay, that brings me to platform types. Has anybody heard of platform types? Ah, 2 people. Okay, great. 3 people. This is going to be fun then. Fun because you're going to hate them. That's awesome. It's gonna be great. So we started the presentation with this snippet of code, and I kind of said, you can have this thing or you can have this thing, and that implicitly implies that there's 2 things. But of course I was lying to you, as any good speaker will do. And there's actually this 3rd representation here. And so we have this idea of something that's nullable, and we have this idea of something that's not nullable, and then we have a 3rd possibility. And what that 3rd possibility means is I have no clue whether you are nullable or not. I really don't have any idea. And so if you're reading this in English, which is my first language, then it acts as English does, which is that if something's nullable, you can think of it as a question. String? Like maybe it's there, maybe it's not. You don't know. Like could be string, could be null. I don't know. The not nullable case, there's no punctuation. It's a statement. This is a string. And then, of course, there's platform types which have no idea what they are, and there's an exclamation point because it's like, oh my god, where am I? What am I? I don't even know. And it's screaming because it has no idea. It's running around frantically. And so, thank you, punctuation. Hopefully that association will stick with you and haunt your nightmares. So, it is important to know that this is a notation and not a syntax. With platform types, you can't say that you don't know anything, which is ironic as a developer because I would love to say that often. But you can't do this. You can't profess that you are not proficient at knowing whether something is null or not. This is generated for you. You might see it in outputs, you might see it in crashes, but you cannot instantiate this platform type. So, when would you get a platform type? Like, what scenario do you not know whether something is nullable or not? Well, not to name names, but some languages do not require you to track the nullability of what you're using. And so you would get platform types when you're working with those languages. Now, here's an example. I have this function. You can look at it. It only returns an array list. There's nothing crazy going on here. And the thing to note here is this line here, and this one too, because you notice that I can work with it as if it's nullable, and it compiles, there are no warnings. I can also work with it as if it's not nullable, and it also compiles and there are no warnings. Now if that seems normal, you can quickly realize that it's not when you compare it to any other Kotlin code. Here, I've created a list in the same way that I was doing in Java. Now, if I work with it as nullable, it correctly identifies that as the correct behavior. If I try to leave that off, it flags it. It says you're going to get an NPE, please don't do this, you need to address this situation. And if I go ahead and switch that type so that it's no longer nullable, well, here it says you're being redundant. Please remove this, you don't need it. So again, in Kotlin, we cannot work with it in both ways. It'll tell us that one way or the other way is wrong. But with platform types, because it has no idea which way is right, it'll let you choose whichever one you want, and you're not going to get any warnings about that. Now, why do you care? Well, this is why we all care. Because, and here's a handy chart for you, if you're wrong, it'll crash. Yay! So that's not great. Because it allows you to work with it as if it's null and as if it's not null, If you say this thing is not null, and you're wrong, and it is null, well, you get your crash. There's a 50% chance that it works out for you in these two cases where you predictably say, okay, it is not null and it isn't null, or it is null and it is null. Those cases work out, and that's great. And then there's, these two other cases where either it crashes or you're doing redundant work. So that's not ideal. Now, you may seem worried by this. I was a little bit concerned, wondering why JetBrains would do this to us. We heard that Kotlin will get rid of NPEs, and now we have platform types and they crash our code if we're wrong. That seems awful. And the answer to that is, well, the language guiding principles. If you're not familiar with them, these are the 4 guiding principles of Kotlin, which is that it should be concise, pragmatic, safe, and interoperable. Now, those are all great things, but unfortunately, when it comes to Java interop, we get a situation like this, where safety would require us to break some of the other language principles. Namely, if you assume in the safest case that everything is always nullable, you have a exponential function for that. So if you have a list, the list itself could be nullable or it could not, and then everything inside of that could also be nullable or not. So a list of a string has 4 different permutations, where both of them are null, neither of them are null, one is null and not the other, etc. And that's a list of strings. That's a pretty simple case. If you get things that are more complex than that, you quickly get this string of possible nullability that you have to go through and unwrap every single time you call anything from Java. And that's not very pragmatic. It's definitely not concise, and it means that you probably are going to hold back from doing any interoperation with Java because it is painful. And so we sacrifice a bit of safety, no worse than what was already in Java, in order to give us these 3 other language principles. Now, you may say, okay, I understand why they did it, but I don't like it, and I would like to not crash. And we have some suggestions for that. So, best practices for platform types: annotate your Java code. The reason for that is if you annotate your Java code, so let's go in here and go ahead and add the nullable annotation like so, you're going to see it is no longer a platform type. The platform type disappeared. It now correctly knows that this is a nullable type, and it won't compile. So if you have not null or nullable annotations in your Java code, platform types go away. They don't exist, because a platform type simply means I don't know whether this is nullable or not. If you provide that information, you don't need this type that says I don't know, because now you do know. Now, we use a lot of things from other people, so if you can't go in and add nullability annotations to your Java code, the next best thing to do is explicitly type anything that you're getting from Java. The reason for that is that if you don't, you will get an NPE like this. And it can be confusing because it doesn't look like anything here is nullable. We don't have the question mark, we don't have any of that, and so you might look at that and say, how is this giving me an NPE? It doesn't look nullable. Now, if you explicitly type the code coming back from Java, you're going to get a much better exception. Specifically, if you go ahead and add a list of string, which is what you're expecting to get back, and it's not that, it'll give you this very nice warning that says illegal state exception. You told me this was not null, but it is null, and it'll point to this line in particular. In this case, it'll point to wherever you first use that thing in the wrong way. So here they're on lines next to each other, but it's very feasible that I get this thing from Java and then I don't use it until 20 lines later. The NPE would be all the way down at the bottom of the file, and you would have to track it back to this source. Whereas if you explicitly type it, you're always getting the NPE at the line that was problematic. So it's not like foolproof, but it's something that can help you at least debug if you can't get rid of them altogether. Okay, recap. The type system is cool. We've learned a little bit about unit, any, nothing, and platform types are dangerous, but we're stuck with them. Okay, so moving on to generics, which is where we would use a lot of these types. I have a little ditty because it's the afternoon, and I want to wake you up, and it goes something like this. A, B, C, D, E, F, G, T is a type param with upper bound, any, question mark. Yay! And what that means is that if you use T as a type parameter like this, the default upper bound is any question mark. Now, there's a question mark there, and yes, you're right. If you don't give any upper bound to your generic t, you have to work with it as if it's nullable. If you don't want to work with it as if it's nullable, go ahead and give it an upper bound of any instead of any question mark, and now you can work with it as if it's not null. Everything goes as planned. Now, a few other things to get out of the way. If you have more than one constraint, normally, if we have one, we would do something like fuzzy, like this, and it would be on that left-hand side. If you have more than one constraint, though, they get kicked out to a where clause on the right-hand side, like so. Nothing crazy going on here, it just helps with readability. Okay, now we get to the fun stuff, type erasure. It's an awful word for a very trivial subject. It's not the worst thing, but it sounds really bad when you read it. So what is type erasure? Kotlin, just like Java, has type erasure. The reason we have it is for performance. If you don't have to keep hold of all the types, then that saves you on your perf hits. What does that mean for you as a developer? Well, if you haven't hit type erasure yet, it means that you get something like this, where if you have some generic passed in, and then at the time you're using it, you try to check what type it is, it's going to say, I can't check the type because I don't know it. I threw that type out. And so I can't tell you whether this is indeed a list of an int anymore. You might say, okay, well, what do I do then? Like, how do I work with this? How do I know if it's a list? And the answer is you use star projections. And what star projections do is they say, I don't care what's inside this collection, just let me know if it's actually a collection. So a star projection means you have no information about a generic at all. And so you can do something like this, if list is list star. And what that means is enter this if statement if there's any sort of list. I have no idea what's in it. It could be an object, a string, an int. Just enter if it's a list. And this is great because now we get to this line, but it's really, really easy to set yourself up for failure with star projections. And the reason for that is that you can enter a list like this and then get overconfident. You said, enter this if statement if it's a list. I know nothing about what's in the list, just enter if it's any sort of list. But if you go ahead then and get confident and say, okay, if it's a list, it must be a list of ints, that's the only thing it could possibly be, and you cast it, the cast will always succeed, always. Even if it's a list of strings, this cast will succeed. The reason it will succeed is because there's nothing there to check whether you are right or wrong. We've erased all of that information. So if you say it's a list of int, well, nobody's there to prove you wrong. There's no type information, so they're going to say, sure, okay, you said it was a list of int. We'll go with that. And that means that later on, once again, you can get errors. Because while this will always succeed, this line here, when you actually go to use it, it'll crash if you're wrong. So be careful with star projections, but they're there if you need them. All right. Now this is where we get into the fun stuff. I mean, type erasure was fun, but this I think is pretty relatable for a lot of people who have been using Kotlin for a little bit of time. It's hard to see on this screen, but you've written an interface, it just has a single function, and you're using it and it works, and that's awesome. And then you see the squiggly, and it says, the type parameter can have out variance. You're like, I have no idea what that is, but it sounds like a great idea. So you add it. Nothing changes. So I guess that's fine. Like, nothing changed. It didn't kill the code. It still compiles, so we'll leave it. Doesn't seem imminently harmful. But you might also then be asking yourself, like, what does this word even do? I don't understand. Like, you told me to add it, and I did, and nothing changed. And so I set up this example to show you what it does. Here, the only relevant piece is that this first function takes t as an argument. The second one returns t, and the third one takes it as an argument and returns it. It does both. Now, I have no constraint on t, and everything's working. If I go ahead and add that out keyword, you're going to see that in both locations that we take t as an argument, we get a compilation error. Okay, we can go ahead and try in. In both locations that we return t, we now have a compilation error. So that's curious. If we have no constraints, we can use it anywhere. If we have this constraint, we can't use it as an argument. And if we have this one, we can't return it. Okay, so cool. We know what it does now. We can move on. Except for that begs the question, like, why do we care at all where t is placed? Like, why does that matter? And the answer is variance. It's telling us something about the variance of the generic parameter. And if you're now asking what is variance, well, I am glad that you asked. I am here to oblige. So, variance tells you something about how two things with the same base type but different type parameters relate to each other. And namely, I think sometimes people get confused and they think that variance is how A relates to B. But it's not that. It's how foo A relates to foo B. Same base class, two different type parameters. Okay, so I'm going to throw a block of code at you. We'll walk through it, don't panic, but here it is. All right, these are all three types of variances. There's only three, so we can get through them, and these are the three. We'll walk through each one. Now, namely, you can go ahead and read this code like you're probably doing right now, but the reason the code is on screen is because the part I care about is the block of red. That's what we're going to focus on. The words don't matter, it's what's lit up in red. So, the invariant case. The invariant case is when we don't have an out or an in modifier. We just say t. And what that means is that it needs to be an exact type match. So you'll see here, I can show you what this looks like. It's just 1, and then 2 extends from 1, and 3 extends from 2, so nothing crazy. 2 has to be assigned to 2. It's the only one that works. If it's not an exact match, they don't compile. This case doesn't compile, this case doesn't compile, it has to be an exact match. Okay, so that's invariant. However, there's also something called covariant. And covariant means that subtyping is preserved. So if A is a subtype of B, then foo A is also a subtype of foo B. Specifically, we see that this middle case continues to succeed. The exact match will always work. But this case is now also succeeding. And we see that 3 is a subtype of 2, so producer of 3 is also a subtype of producer of 2. That is our covariant case. And the last one is contravariant. Now, the beginning of that word should give you a clue. Contra, in contrast to, it flips the subtyping. So, if A is a subtype of B, we flip it, and now foo B is a subtype of foo A. It's not intuitive. So anytime you see contra, just think, whatever I thought it was, I was wrong, I'm going to do the opposite. And you'll probably be right in that case. So, again, this middle case, it works. It will always work. That's the invariant case. But now we see this flipped case, which is that 1 is a supertype of 2. And so consumer 1 is now a subtype of consumer 2. They're opposites. That relationship is inverted. Okay. That's still a lot, but to put that into English words and like put it in a sentence that hopefully is a little bit more parsable, why do we care about variance and why do we care about where t is in out relationships? Well, it's because out means that it is covariant, which means that the subtyping is preserved. Now, we can only ever make that guarantee if that t parameter occurs in certain locations. If it occurs in other locations, that promise is broken. Ergo, out means that we constrain it to those producing locations. Now, on the other hand, in means that it's contravariant, which means that its subtyping is flipped, and again, we can only make that promise if t occurs in given locations, which is why the in keyword makes it so that we can only use t in those consuming positions. Okay, now that still doesn't tell you why we actually care. And the reason for that is because in a world without variance, life is really tedious and it's not much fun. Specifically, we always have to have exact matches. So mutable list, you both read to it and write to it, so it's the invariant case. There's no out or in keyword here, which means it always has to be an exact match. So specifically, you cannot assign a mutable list of strings to a mutable list of any. Now, that makes sense for mutable lists because we're reading and writing, so we want to make sure we're reading and writing the exact same type of thing. But if we're reading something only, as in a list case, it's really, really annoying if we can't assign a list of strings to something with the type list of any. That doesn't make much sense. And so, indeed, if you go in and look at list, you see that it has the out parameter on the e. And that's why this code works. We can assign a list of strings to a list of any, and this is safe. So the TLDR on variance is that it allows us to be more flexible without giving up any of the safety that we know and love of the language. And this is a big caveat to variance, which is that it exists to protect you from everybody else in this room. Unfortunately, it does not exist to protect you from yourself. You're going to have to find something else to deal with that. And what that means is I've set up this example where I have one parameter that has in, one that has out, and one that has neither. And again, the only thing on this slide that matters is not the words, it's what's lit up in red. So specifically, a constructor is neither covariant or contravariant. I can use all of these things and they're not lit up in red. A val, which is public in this case, public by default, it has a getter. And so this in marked t is failing. And likewise, a var is something that has a getter and a setter. It uses it in both the in and the out locations. So both the in and out versions are breaking. Okay, so that's fine so far. Now what I've done is I've copied this entire block and I've pasted it here. And the only thing I've changed is I've added a private keyword to all of those. And you'll notice that none of them error anymore. So if I take it off, we get the same error. If I put private, we don't. And that's because, again, variance describes that outer communication that you have with people consuming your code. It doesn't apply to anything that's private or internal to that class. Now, the same thing applies to functions. I have just created a bunch of permutations. If I remove private, we get the same error that we would expect. If I add it back, it all works. So all of this is to say that generic applies to people, that variance applies to people consuming your code. It does not apply to you with private internal state. Okay, now, if you've heard anything about variance in Kotlin, it's probably that Java has use site variance and Kotlin has declaration site variance, and those words probably mean nothing to you, so I'll tell you what they mean. Specifically, declaration site variance is nice because here I am declaring t, and I'm also telling you what its variance is. It has out variance, it's covariant. And so that means that when I go ahead and use it, I can use it. I don't need to do anything. I just say, okay, a small dog is a subtype of dog, so I can assign this. This is great. Now, in Java and Kotlin 2, you still have the ability to do use site variance. And what that means is if I build some class, the invariant case, it's not modified in any way, then at the point at which I use that class, I can give you information about its variance. So here, I've added the out keyword, and here I've added the in keyword. Now, once again, if I remove them, it doesn't compile, because it would have to be an exact match if it was invariant. But if I do this use site projection of the variance, I can now assign something that's int to something that's number. Likewise, with the in case, if I have nothing, it's a compilation error. But if I have this use site projection, I now get that extra latitude to assign a number to an int. Okay, so if you're familiar with Java generics, it's worth noting that these are equivalent. If you need a way to remember this, you can look at the acronym PECS. PECS is how I pronounce it in my head. I don't know how you would pronounce it in your head, but it basically says producer extends consumer super. And what that means is that this out keyword, same as question mark extends t, the in question mark super t, these concepts are not new. They just have a new way of expressing them. Okay, now, why do we care about all of that material we just went through? Well, because Kotlin, by default, it ships you a lot of these things without projections, those read-only projections. Namely, you have a mutable list, and you also have a read-only list. They give you that for free. As you saw in the definition that I showed you, list, the read-only version, it's just the mutable version with the out keyword assigned to the generic. So they're not going to ship that in every different way you want it, but you can easily create your own by using variance. Add the out keyword, now we have that read-only behavior. So, okay, let's wrap that all up with a use case. We have talked about types, which led pretty naturally into how we would use them in generics. But I just talked for a while about generics, and you might be wondering why you care. And I have an answer. I always have an answer. So here is a simple standard library function that you might use. It's a map. I've created an array, it's empty, so map actually won't do anything. But if I go in and look at map, it has generics. Yay! So they're useful. We use them places. But if you go in and look at it even further, you'll notice it has types and it has generics, and it also has this word, inline. And if you're a curious type of fellow, you might wonder, what is the deal with inlining? Well, let's build an example to find out. The key to this is that it has 3 steps, 2 of which don't matter. So the first one, we can create an array of the numbers 1, 2, and 3. That's it, nothing crazy happening. The last one, we're printing it. Again, nothing crazy there, we're literally just printing that. Now, the one in the middle is the one that's interesting because we just saw that the definition of map is inline, and that's what we want to explore. So what is this line doing? Well, with the lambda, it says take the numbers 1, 2, and 3 and map them to that plus 1. So what you're getting out on the other side is an array of the numbers 2, 3, and 4. Just each one had a plus 1 added to it. So that's what it's doing. Now let's take a look at how it's doing that. If you go in and decompile the code, you're going to get something that looks a lot like this. Now it's completely unreadable and you probably don't want to look at it any longer, so I've gone ahead and I've cleaned it up. And this is like what you would get if you decompiled it but then tweaked it so it had better variable names. And basically that map with the plus 1, it's creating a new array list, and then it's getting the iterator of the one that you want to map, and it's going through each of those values, adding 1 to them, and putting them into that destination array which it's going to return. So nothing crazy, we're going through a list, adding 1 to each value and storing it in our output, returning the output. That's what that map is doing. Okay, so if we want to know what inline does in the context of this example, we can go ahead and decompile this whole function. Again, it's just the creation of the array, that inlined function, and then the print. So, oh yes, we can look at the generated code. It looks like this, which again is really, really ugly and we won't spend time on, but it's here if you want to look at it. And so the cleaned up version is this. And now we can finally see what that inline is doing. Namely, this line here is exactly the same. We created an array, yay! And this line here is exactly the same too. The only thing that has changed in that is that all of that code that we saw that map is doing, it's now in our function. It's here. This is an exact copy of what the map code we saw earlier was doing, but now it's inside of our function. So to answer the question of what inlining does, well, it injects code directly into the call site. And specifically what that means is that if we have a function who does exactly one thing, it prints a line, then what you're going to get is this foo with the function invocation will turn into foo with that line injected. It's no longer redirecting to another function and then printing. It just takes the contents of that function, plugs it into the call site, and that's what you have. Now it's worth noting that this applies to both lambdas and functions. So here we've changed our say hello to have a println, exactly like the first case, but also a lambda. And what that means is that when we go here and we have this inline function, it turns into the inline like this. Now specifically, if you're wondering how we generated this, well, this is the definition of our function. So we can copy it in. That's what inlining does. And now it applies to lambdas too, so all we would do is go ahead and copy in this and open this up. This is what we get, which is exactly what you saw earlier. That's how we created this method. I have an extra bracket somewhere, but that's fine. Oh, I have a missing bracket somewhere. So this is how we created the function. We copied this, and then there was a lambda, and then we copied the contents of the lambda, and now we're here. That's what inlining does. Okay, you might ask, well, okay, why not use the function? Like, we had a perfectly good function, and then you copied it into another one instead of just calling the function. That's a little bit weird. Well, the answer there is performance. It's always performance. Anytime something is weird, it's performance. That's like the #1 go-to. And specifically, it's the performance of lambdas. Lambdas have overhead, and what inlining does is it tries to get around the overhead of the lambdas. And that's a little hand wavy, and it's hand wavy for a purpose, which is that it would take a long time to go into that. But if you're curious, you can definitely look it up. And the way you know that I'm not lying about it, even though I'm not going into it, is that if you hover over an inline function that does not use a lambda, you're immediately going to get this warning that says, hey, using inline with anything that doesn't pass a lambda is not very useful. You're really not going to get any benefits. You can do it, but you're not getting anything from it. Because again, this inline is aimed at lambda overhead. So, we talked briefly about the who, what, where, why, and when of lambdas. Namely, they're inline. Inlining means you inject code into a method. You do that via the method signature. Why do we do it? Because of performance. And when do we do it? When we're using lambdas. Now, I left off this one keyword, which is how. And if you're wondering, are there special cases to inlining that I should be worried about? The answer is, of course, yes. For instance, you usually don't want to inline lambdas that are very large. The reason for that is that it copies all of the code in that lambda into every different place that calls it. If it's 60 lines of code in a lambda, every place that invokes that lambda in an inline format will have all 60 lines copied and pasted, so that can lead to code bloat. Now, there are more reasons, like these words, cross-inline, no-inline. I haven't talked about them at all. And they're scary and a lot of people don't like them because they're a little bit complex. And unfortunately, because of that, I won't be able to do them justice if I talk about them today. However, I don't want to completely leave you hanging, and so I've provided a link to the documentation that explains these caveats, and also this is a jumping off point for Google. A lot of times, if you are trying to get into a concept, it's hard to know which keyword to look for in a search engine. So I've provided those. If you want to learn more about inlining, 3 things that you probably want to know about to make sure that you're doing it properly is reified generics, cross-inline, and no-inline modifiers. I've given you recaps of why you would care about these, but I'll post the slides and you can go and Google those later. I'll also cover them in a talk in the future when I can do them justice. But for today, that's all I have for you. Thanks for coming to my talk.